Okay, welcome to part 2 of thermodynamics. So these are objectives for this part. We're going to understand heat transfer. So remember, heat transfers are enthalpy and changes in entropy. We're going to do some calculations, and this will be primarily in our Zoom meeting where we do calculations. We're going to introduce this new energy term, Gibbs free energy. And Gibbs free energy is really combining enthalpy and entropy together and also considering the temperature. We're going to pull all those pieces in together into one equation that gives us this Gibbs free energy. And then there's various ways to calculate Gibbs free energy, so we're just going to go through the 3 different ways that we can calculate Gibbs free energy. The math is not terribly difficult, it's just kind of keeping track of enthalpy, entropy, and now I'm introducing big G, which is Gibbs free energy. All right, before we do that, let's back up a little bit and just review our enthalpy. So remember, this is the heat of the reaction. We report this as big H, it's a state function. And if I want to determine the change in enthalpy of a reaction, I could look at the change between my reactants and my products, because delta H means I have some final state minus some initial state. And my sign of delta H is going to depend upon which one of these had greater amount of energy. If delta H is positive, then it's endothermic and I'm adding energy in. If delta H is negative, then it's exothermic and I'm releasing energy. So for delta H to be negative, my initial energy has to be greater, my initial enthalpy has to be greater than my final enthalpy, which is what we see. And so that difference here is the energy, the thermal energy that's being released to the atmosphere. For a chemical reaction, I would take my value of my enthalpy, whatever C is, and I would multiply that by 2, and then I would subtract 2 times my enthalpy value for A plus 1 times my enthalpy value for B. And that would give me my change of that reaction. So if this is larger than this, meaning this is all this here is my initial enthalpy and this is my final enthalpy, then that's going to determine my sign for delta H. So I can do the exact same thing for entropy. I can have delta S, I'm looking at my final state minus my initial state. If I want to apply it to a chemical reaction, I could apply it to reactants and products. So let's say I still have this same thing up here. My delta S for this reaction is going to look very, very similar, only instead of my enthalpy values, I'm going to have entropy values. Initial, and this would be my delta S. And so my sign here is going to depend, and remember, I'm going to be different. So here, this is favored if my enthalpy is negative, because that means that my energy is leaving the system. Here's my heat. My final product has lower energy than my initial product because heat has been emitted. Here, I want to increase the entropy. So I want my value to be higher. When delta S is positive, that's going to be favored because I've increased the entropy of that system in whatever final state I'm in. So I want this to increase, I want this to decrease. So we calculate them very similar, but the signs are going to tell us whether it's favored or unfavored, what's happening in that system. We'll do one problem together. Let's say I have NH3 plus 5O2, this is a 5, not an S, 4NO plus 6 waters. I want to calculate delta S for this reaction. I can predict just by looking at this what the sign is going to be, because here I have 9 moles of gas and here I have 10 moles of gas. So this is going to be favored. So I would expect my change in enthalpy sign to be positive. So I already know just by looking at this chemical reaction that it's favored from an entropy standpoint. I don't know anything about the enthalpy unless I'm given the heat of the reaction or I look up these values. I can find these values in a table in my book, and that table looks like this. And so this is the appendix 2 in the back of your textbook. And we're going to get to G today. This is Gibbs free energy. You see I have values of enthalpy, and this little small f means enthalpy of formation. These are the absolute values for the formation of that. So this means if potassium is a solid and it has 0 heat of formation, that means that that is its most stable state. There isn't going to be a heat transfer to form that because it's already been formed. But entropy, remember, everything has a positive entropy. So you're always going to find a value for entropy, even if you don't find a value for enthalpy. And so here you see that my enthalpy values are all positive. They are always going to be positive. whereas my enthalpy values are going to be positive or negative depending upon whether it's favored from an enthalpy standpoint or not. So these are always going to be positive. So I'd look these values up, then I can plug those in and solve for my change in entropy. If I were to look at these values, what I find is that this is 210.8 joules per mole Kelvin. NO is 188.8 joules per mole Kelvin. This is going to be, I'm going to have a value for oxygen. Oxygen is 205.2 joules mole Kelvin, and ammonia is 192.8 joules mole Kelvin. So I would just take these values. These are all my SF values that I looked up in the table, and then I could plug them into this equation here and solve for delta S. So delta S of my reaction, and since these values all came from a table under standard state conditions, then I'm going to note that my calculation is going to reflect that these are under standard state conditions. So I have 4 moles of that, and this is 4 moles, and this is going to cancel my moles, so my units out of this are going to be joules per Kelvin, because my moles are going to cancel out. And that's going to give me my delta S for this reaction is 178.8, and my units are joule Kelvin. And it's positive, which is what I would predict because I'm forming more moles of gas. So this is going to be favored from an entropy standpoint, and I see that here. And I could do the same thing and find my enthalpy, and then I would know if it's favored from an enthalpy standpoint because I could look up these values and do the same thing here. If I get a negative value, then it's going to be favored. If I get a positive value, it's not. All right, so our second law of thermodynamics dealt with spontaneity. For a reaction to be spontaneous, that the enthalpy of the universe is always increasing. I can distill this down a little bit more and determine if I'm talking about the entropy of my system or the entropy of my surroundings. And the addition of these is going to equal your delta S of the surroundings. So if delta S of the universe is positive, then that process or that reaction is going to be spontaneous. If delta S of the universe is negative, then it's going to be non-spontaneous. So S is my criteria for spontaneity, specifically S for the universe. So this could be negative and this could be positive. These aren't always going to be the same. This could be negative or these could be positive, but your absolute values are what's going to always be positive. So both of these are going to play a role in the spontaneity of a chemical reaction. So we're going to take each one of them separately. We already looked at S of the system. And S of the system, these are these things where when we looked at changes in physical states, solid is going to be less than a liquid, which is going to be less than a gas. And we talked about molecular weight and molecular complexity. And in a chemical reaction, I'm going to favor the side that forms more moles of gas. So if I produce more moles of gas in my products than I have in my reactant, then that's going to be favored from an S standpoint. These are all the systems. My system here is, what is it that's in that physical state? What is that water? The water is my system. What is the thing that I'm looking at in terms of molecular complexity? NO versus N2O4, this is my system. And that's what I'm looking at. So these would all be things where I can predict what's happening with the entropy in relation to the system. The surroundings is going to be a little bit harder. And we can relate the surroundings to delta H. And so we're going to relate the surroundings to delta H, and we're going to do it in this equation here. So delta S of the surroundings is going to equal negative delta H of the system over temperature. So this is going to be temperature dependent, and it also depends on the change in heat of the system. This is what this is. This is my delta H for my system. So if my process is endothermic, delta H is going to be positive, and my delta S of my surroundings is going to be negative. That means it's losing entropy. If my process is exothermic, delta H is negative, delta S of my surroundings is positive, and it's gaining entropy. So if you think about what this is, H is the transfer of heat. So if I have a process or a reaction where heat is being transferred to the surroundings, then everything that is in that surroundings is going to absorb that heat, and it's going to be related to kinetic energy. The air molecules that might be be in the surroundings. They're going to absorb that heat. They're going to start to move faster. So that increases their entropy because now they're moving more. I've increased their degrees of freedom, their randomness, their disorder. And so anytime I have an exothermic reaction, I'm losing energy from the system in the form of heat, but I'm gaining energy in the surroundings in the form of entropy, or vice versa. If I have a process that's endothermic, now I'm pulling heat from the surroundings, which means the surroundings is going to lose entropy. The system here is related to the entropy of the surroundings because heat is always going to change the movement of things that are around it. And so I can relate this, which I can't really calculate. I can't look and determine what's happening. I can relate this to my enthalpy using this equation here. And so this allows me to take this and this into account and then be able to determine if my entropy of the universe is going to be spontaneous or non-spontaneous. And so that process that I'm looking at, is it going to be a spontaneous process or non-spontaneous process? I'm going to look at S of the system, and I'm also going to look at S of the surroundings by looking at H of the system. So those two components are going to allow me, I'm going to pull those together. That's going to allow me to determine overall whether something is spontaneous or not. Let's just do a quick example here. So let's say I have this reaction. Nitrogen gas reacting with oxygen gas to produce dinitrogen monoxide gas. And I want to know, is this going to be a spontaneous reaction? Is it going to happen spontaneously? There's two components, right? I'm going to have to look at my delta H of my system, and I'm also going to have to look at delta S of the system, and those are going to tell me if it's spontaneous or not. So I'm going to take each one of these separately. What I give you for this is that I give you the delta H of the system is, if I were to calculate this, 163.2 kilojoules. So this is an endothermic reaction. So it is endothermic, meaning that it's absorbing heat from the surroundings. So my delta, my surrounding, is going to be negative. So this is going to be unfavored from an enthalpy standpoint. So I can go ahead and calculate that. So my delta S of my surroundings is going to be equal to negative 163.2 kilojoules over, and the other piece of information I need to give you is that this is at 25 degrees. At 25 degrees Celsius. So I'm going to change that to Kelvin, 298 Kelvin. Now, entropy is always going to be in units of joules. So I'm going to convert this to joules by multiplying by 1,000. Now this is going to give me a delta H of the surroundings. It's going to be negative, which I would expect because this is positive, of 548 joules per Kelvin. So this is not favored from the surroundings. So what I don't know is it going to be favored from the system? So the system, if I look up here, what I see is I have 3 moles of a gas. I probably don't even need to do any calculations. I'm going to 2 moles of a gas. So my delta S here, if I work that out, that's going to be negative because this is going to be not favored. So in this case, this is negative, this is negative, this is going to be negative, and it's going to be non-spontaneous. I could go and calculate delta S. So if I went and looked up the values and calculated delta S, I would get these values here using my table, also non-spontaneous. And then if I wanted to calculate delta S of the universe, I would just plug these two values in. This value here, which is going to be negative, so it's going to be non-spontaneous. And I considered both of these. So this allowed me to find what's happening in the surroundings, and this allows me to find out what's happening in the system. All right, so this is a lot of work to go ahead and calculate this and then pull this in here and then look at this. So it would be really nice to have a way to kind of shortcut that. And that's what Gibbs free energy is. Gibbs free energy. And it takes into account both the enthalpy of the system, so H of the system, and my entropy of the system, right? Because those were the two components that I was looking at here to figure out if I had a spontaneous reaction or not. I'm looking at the enthalpy of the system, the entropy of the system, and then I'm relating the enthalpy of the system to the entropy of the surroundings, and then that's allowing me to determine if overall what's happening to the enthalpy of the universe, is it decreasing or is it increasing? If it's decreasing, it's negative, then it's non-spontaneous. So this is going to allow me to not have to go through all that, because it's going to put these into one equation. And we're going to relate it to this new energy term called Gibbs free energy, capital G. This is also a state function. It combines H of the system, S of the system, and temperature. So it's going to combine all three of those together. And the equation looks like this. So this is my reaction here for Gibbs free energy. I'm going to look at the change in energy of the system equals the change in enthalpy of the system minus the temperature times the change in entropy of the system. And remember, we have a unit issue here. So this is going to be in units of kilojoules, and this is in units of joules per Kelvin. My temperature is going to have to be in units of Kelvin. When you calculate G, G is going to be in units of kilojoules. So before you take this component here and you apply it to the enthalpy, you're going to have to change your units to kilojoules from joules. So that's just one thing to keep in mind, is even though these are all energy terms, you're going to look them up in the same table. You're going to find these terms in the table. These are going to be in units of joules. These are in units of kilojoules. So don't get hung up on that. So if I take this equation and I look at it, what this means is that at higher temperatures, enthalpy is going to have a higher effect on the spontaneity of a chemical reaction than it's going to have at lower temperatures. And so this is very temperature sensitive here. So at higher temperatures, S will have a bigger effect. So let's get through some of the scenarios. Some of the scenarios in terms of signs. In my first one, I have a delta H, that's a negative sign. So this would be an exothermic reaction. It's favored. And let's say I have a delta S that's positive. This means that I'm increasing the entropy of the system, and that's also favored. Then if I plug these in, then delta G is going to be equal to my delta H is a negative minus T delta S, and S is positive. This value is positive. This value is negative. Then I'm going to have a negative minus a negative, so delta G is going to be negative. That means this is going to be spontaneous at all temperatures. So it's not going to matter what the temperature is because it's favored from an enthalpy standpoint and it's also favored from an entropy standpoint. Let's say I have a scenario where now my delta H is positive. So this is an endothermic reaction. It's going to be unfavored. So delta H is greater than 0. And let's say delta S is negative. This means I'm decreasing. This is also unfavored. So my delta G then would be equal to delta H, which is a positive value, minus T delta S, which is a negative value. So this makes this a negative makes this positive. So delta G is positive. This is going to be non-spontaneous at all temperatures. So for spontaneity now, I'm going to define it in terms of delta G because that's going to allow me to take into account my S of the surroundings, my S of the system. If delta G is negative, then it's spontaneous. If delta G is positive, it's going to be non-spontaneous. Now what happens if I have a mix would be delta H is negative, so it's favored, but delta S is negative. It's decreasing entropy. So now if I plug these in, delta G, this is negative, so delta H is negative minus T delta S. Delta S is negative, so this whole thing here is going to become positive, and then the sign of delta G is going to depend. It's going to be temperature dependent. So this is where if I have a high temperature, it's going to weight my entropy much higher than my enthalpy. So at high temperatures, it's going to become unfavored. So it's going to be non-spontaneous at high temperatures. The more this weights this factor. My fourth one is if delta H is positive, so this is unfavored from an enthalpy standpoint, and delta S is positive. So it's favored from an entropy standpoint. Now what my delta G looks like is delta H is now positive minus T delta S, and this is positive. And so once again, this is going to be weighted. The more that this increases, then it's going to be spontaneous. So this is temperature dependent on the sign for delta G, and it's going to be spontaneous at high temperatures. So we could say non-spontaneous at low. And up here we could say spontaneous at low. So these are our two scenarios where it's going to be temperature dependent. All right, really briefly, there are 3 ways to calculate delta G for a reaction. The first one is if I have delta H and delta S, I can calculate delta G that way, where I calculate this separately using the table in the book, and then I calculate this separately using the table in the book, and this is my temperature of my reaction. So I can calculate delta G that way. So I can also calculate delta G using the tables in the book. I'm going to sum up the Gibbs free energy values of formation for my products minus the sum, and in here is the stoichiometry for my reactants. So just like I did with delta H and delta S, I can do the same thing with delta G, because in that table, when we looked at it, I had standard state values for this for formation, I had standard state values for this for formation, and I also had standard state values for this for formation. So I could do it that way. My third way is if I have a stepwise reaction. My overall delta G for that reaction is equal to the delta G for each individual steps. So let's say I have reaction number 1 and reaction number 2 and so forth. So if I had a reaction that occurred in 3 steps and I knew the Gibbs free energy value for each of those individual steps, I could add them up and get to my overall. And this is what we're going to be doing some calculations on when we come together in our Zoom session for this part. So this ends part 2, and then we will come back together and do part 3.